And yeah, today we will hear about the computational gradient flows. And yeah, please go ahead and thank you for coming.
Thank you, Thomas. And yeah, it's very happy to be in Japan. And I'm originally from Asia, so over the years I did not give many talks, less than 5 talks in Asia probably. So this always happy to be here. Today I will talk about gradient flows. A lot of things I've been working on over the past couple of years, and mostly with hope of applying it to computational research. So for a lot of you in the audience, I know probably from different disciplines. Some of you are from machine learning. Some of you might be, because we're in Japan, from information geometry. If there's anything you would like me to explain more, and I can also speak different languages from different languages, meaning in your discipline, right? But 少し日本語できます。I can also speak different languages. That's also fine. So I'll talk about applications in inference sampling optimization. Okay, some overviews, just get it over with some very popular topics such as generative models. Nowadays, everything is about generative models. About a lifetime ago, generative models is more like a static optimization problem where you try to minimize the divergence between some generated data versus the data you observe. And if your divergence, if you train a generative model which transform latent Gaussian simple distributions into some complex distribution that's very close to the data, you think about generative model is doing a good job. That's a while ago. But nowadays, people do more complicated generative model because they realize that just writing down the static optimization problem was not enough. You have to look into design a specific optimization algorithm that works well, the probability or say the optimization path that works well in practice, right? So that's why nowadays the generative models, a lot of those are based on dynamics or based on simulating ordinary partial or stochastic differential equations. For example, everybody knows the diffusion model, try to using the noising process to turn data into noise, then eventually hope is to reconstruct the data. Some of those are based on these so-called flow. Basically, the right-hand side of the ODE is the flow. And if you can simulate this ODE, you can try to take every image or take every noise and evolve this ODE into a data point, right? So this is one motivation for this talk. Another motivation, I think just made the slides for you guys. I don't have to variational learning there. I don't want to explain what's variational learning because to me, it's still, I can only sell you secondhand. You guys know more about variational learning. But sort of my perspective is if you try to minimize a function, in the past, you have optimization problem. Of course, don't blame me if I'm making it wrong because I have no Bayesian training whatsoever, okay? Instead of looking for a single minimizer, you look for a distributional minimizer. In this regard, you can write down the optimization problem as not just empirically minimize with respect to the hypothesis theta, but minimize with respect to the distribution of data. Okay, we seek a distributional optimizer. Yeah, I think this is my understanding, but you can tell me if it's not variational learning. So yeah, and so many figures from many of you there claiming, not my claim, your claim that this really solves real world problem better than Atom and a lot of state-of-art algorithm, right? So my point of using this slide is just to say that this is also a perspective to motivate, just like previously we're manipulating probability distributions for generative models. Here we're manipulating probability distributions to identify a good optimizer for a machine learning model. All right, last but not least, there are some other cases when in the past I worked with, if you want to minimize, if you want to fit a red curve nicely with a linear regression, right, somewhere you have to compromise because you cannot fit everywhere nicely. In the specific case, if you have the training data and the tested data is the orange data points, if you want to do well, so if you concentrate on the left part of the data, maybe you will not do so well during the test time, right? So this is somehow the distribution changes over training and test. So this, again, the changes of distributions, we need to understand it, for example, in what so-called geometry is the distribution changing, right? You can describe the change of distribution, the epsilon change in distribution with, for example, KL divergence or Wasserstein distance and so on, or even talk about some kernel methods, particle systems, describing such changes in distribution such that we can learn robustly accounting the changes of distribution. Okay, so my goal is to really studying all these things is for a general purpose optimization algorithm over probability measures. This is the overarching goal, okay? So the types of application I've been talking about so far, they all fall into such paradigms. The goal is to model a probability measure or measure pi. What I usually have access to the target pi is either I have the it's samples. I can get samples from the target. This is the case of generated models, okay? For example, I get to see pictures of dogs before I generate. Or in some inference tasks, for example, in variational learning, what I have is score function, okay? I get to evaluate this log pi function. It's sort of like an oracle model. I get to evaluate it. You give me an x, you give me an x where this x is, I'm gonna tell you what log pi x is, right? This happens when you don't know the so-called partition function. Okay, and as an output, my algorithm should give it back to you either new samples, the samples you have not seen before from pi, or an approximate distribution of pi in the sense, in the form of a parameterized family, okay? So overall, the goal is to model pi. And like I said, my overall mission is to turn this into an optimization problem. This is the overarching goal, okay? I hope that pi can be the solution of an optimization problem. And this is the very high level thing. I've not talked about gradient flow or any specific analysis topics. And the goal is to construct, just like classical optimization algorithms, you do gradient descent. But every iterate here is a probability distribution. Okay, so this is, I guess this is not variational learning. This is not Bayes. This is just optimization problem over probability distributions. Okay, and it's a direct optimization problem. And sometimes I work in the space of positive measures, depends on my needs. And sometimes the application would dictate what space I work at. Sometimes I stay within a subset of the probability of the measures. And sometimes I work with simplexes, basically discrete probability measure. Sometimes I work with continuous measures. Sometimes I work with normalized measures. You know, discrete, continuous. This is normalized measures. And if you get out of this simplex, you work with more general cone of positive measures, non-negative measures. Okay, canonical example is familiar to everybody here. It's the so-called Kullback-Leibler divergence, or say the Boltzmann-Shannon entropy. It's an integral of the convex function of the Radon-Nicotin derivative with respect to this reference measure. Yeah. So, and you can change this phi a little bit, as many of you know. This is, I'm plotting this phi function, but if you curve it up a little bit, curve it down a little bit, you get different kinds of so-called relative entropies. And the missing ingredients of so far what I've written down on this slide is that we must respect the geometry of probability measures. So I plotted a lot of spaces, and we've then we have to build the notion of distance or geometry between two probability measures. We can use information geometry, or we can use things like optimal transport. Okay, so for many of you, this the following will be a very high level review. Okay. By the way, please ask questions when it comes to it. Yeah.
Sorry. So
yeah.
You don't want to distract you.
Oh no, not at all.
The gradient flow that you've got, but I was wondering, if so from a machine learning perspective,
right?
We often criticize optimization people if they focus on a general problem instead of thinking about, test errors and stuff like that.
Mm.
So that was a big loss, I think, at least in the past.
Mm.
And I don't know if it's the case here as well, because when you say optimization over probability distribution, that's really too broad. All Bayes is included in that.
Oh, okay, good.
Right. So depending on when you specialize the problem, you start to do completely different things. Right. So you do evolutionary algorithms or distribution robust optimization.
Yeah.
Or you do Bayes. They're very, very different algorithms. And why would we think that taking a too general formulation, will it be insightful? I mean, I think at some point, at some level, it will be. But why do you work on this thing, and how do you plan to avoid these issues?
Great. Yeah, thanks a lot. I think this is a really good question in the sense we should first decide whether the topic is useful or not before we invest the years to work on it, right? So it's important to ask this question. For me, the initial motivation is actually backwards. I was initially working on very specific things like you were talking about. And then what I found out is there turned out to be already a lot of theory in mathematics already have studied these problems, have very advanced results in analysis. So now my approach to deciding what to work on has been either I cover my eyes and pretend that didn't exist, invent new theory, and try to sell it to the world and give a talk shamelessly to some people who are more experts than I am. Or be a good student and kept on learning and figure out what's there that can actually be applied to machine learning problems. So I took the latter, otherwise I wouldn't be talking about these topics here. The reason why it has to be so broad is because I really want to make the connection that directly optimizing over distributions, this is doable with, or is becoming doable with the modern analysis tools. It was not doable back in the time of, I mean, arguably, I say not doable, computational analysis wasn't back in the times, probably Fisher and so on, right? A lot of problems are about changing probability distributions, but I would say back then, people's understanding was not generally venturing into the measure space, but more looking at parameter estimations and different algorithms for parameter estimation. For example, we invented EM algorithm. And later on, even till today, there's every couple months, there's a new paper about the interpretation of EM algorithm. So this would be sort of the way I'm thinking about the problem is I take, initially I was working on specific problems, but I take a stance back to see that there is actually, you have direct tools in the so-called variational methods, optimization analysis, to actually directly work on optimizational measures. So whether or not later we have to tailor it to specific problems, of course, yes. But now we have to first set a ground solid. There is mathematical foundation for those. We don't have to invent those. So I'm still, this talk mostly based on mathematical foundations of things. Definitely there needs to be more people working on specific things for every specific topic. Fantastic question. I already feel I'm at a job interview situation. What am I doing with them? Good. So, okay, sorry. Took some time to discuss this, but let's get back to some, like I said, for many of you, this will just be a very brief review because many of you have different expertise overlapping things here. First, I just, in the interest of time, because I want to get to the meat of the talk. But now I'm just going to define things like optimal transport distance in a very intuitive way because I've talked about this thing so many times in my life. I don't want to go through this math anymore. What I define is the p-order Kantorovich-Wasserstein distance. The idea is to, if you have two samples, this generated from the red distribution, this generated from the blue distribution. The distance between these two probability distributions defined as, on the top, just as the Euclidean, average Euclidean distance between them, okay? That's it. So that's the simplest distance possible because if you just take two simple points, the Wasserstein distance recovers the Euclidean distance, okay? Now, of course, if you have more points, you have the question, right? If I have 5 points here, 2 points here, then how am I going to match them to take the average, right? So then it becomes the question, you have to relax this problem into such a problem called the relaxation of the Monge problem to a Kantrovich problem, where you measure the distance between a discrete distribution to a continuous distribution. By figuring out there's a joint distribution, there are many joint distributions that agree with them. I pick one of them that has the least amount of this quantity, which is defined as the value of the optimization problem. The minimization of this cost function over this joint distribution. This cost function is the piece order of the Euclidean distance. And this joint distribution has to be constrained to have the marginals of these two marginal distributions given. So this solution or this value of the optimization problem is the Wasserstein distance. And what's usually really relevant to what I do is also really relevant to people in geometry and so on, is this almost like Riemannian formulation of the Wasserstein distance. Been shown that you can view it as a very abstract way to think about you walk on a manifold that's almost manifold, row 0 towards row 1. And every time you have a cost, like a cost of an optimal control problem, you can take many different paths. The path with the least cost, or say the shortest length, and on this manifold, observing or say restricted to a certain kind of dynamics. In this case, all I can do for probability measures is I can transport the mass. I'm not allowed to throw them away and create it here. If I'm only allowed to transport, the shortest, the most efficient way, the least cost way to transport from all the points here to all the points there, the amount of work you do is the Wasserstein distance, okay? Can be succinctly written as the so-called dynamic formulation of this geodesic distance. Okay, what I write here is the squared distance. You can also generalize the p order distance, although it would have less of a structure like a Riemannian manifold. Okay, I'm going to talk a little bit about this distance. I will refer to this specific distance as the Hellinger distance. There are also a lot of people referring to Fischer-Rao. It's just so during my talk, when I talk about this guy, I mean the Hellinger. The reason is that when I move from one distribution to the other, sometimes I do not have conserved mass. I sometimes have more mass and have less mass. Okay, it's very understandable because you can think of a transport problem if you want to move from one place to the other. One way is to destroy all the mass and create it somewhere else, right? In this destruction and creation phases, maybe the speed of destruction does not match the rate of destruction does not match the rate of creation. And this time, you do not have the probability distribution. You have a positive measure. The dynamic formulation you can also written down in the manner of the Wasserstein. It's just the dynamics now. It's the reaction ODE instead of the partial differential equation with transport PDE we have seen before. And for this Hellinger distance, it has a closed form expression instead of the Wasserstein distance does not have. This is simply the L2 distance between the square root of the density. I'll just take the reference density as the big measure. And you can apply backwards a lot of Wasserstein terminology paradigms into studying this. You can write down the geodesic curves and so on. I just wanted to give you a little bit disclaimer because I'm not studying the geometry of exponential families. I'm simply studying the geometry of densities or say full measure space. That's why I call this the Hellinger distance. You could call it the Fischer-Rao distance if you consider the mu as a parameterized for itself, okay? But now I'm not really doing any exponential family, just general measure space. They can be, in a way, discrete measures. There also works on discrete to continuous, and in a way, something. Yeah, you can also write in as a dual form, the so-called variation. Okay. Yes. Yes, so, yes.
And the subsets in the probability measure.
Yeah.
They are not like very specific, like convex and compact or whatever?
Yeah, so this first is to define a distance notion between two probability measures. And in this case, I do not restrict myself to Gaussian or to exponential family. So mu0 and mu1 can be none of those subsets. It could be outside these subsets. So I'm working on general measures.
But they're not defined in the whole space always, like, you know what I'm saying?
Whole probability space. Now I'm
maybe it's irrelevant right now, if they are on subsets or not.
No, it's not really. I allow you to pick anything outside your usual exponential family and so on. You can pick something that's not exponential. You can pick things outside the usual Fisher-Tropsch manifold. Yeah,
definition is actually very general.
Yeah, it's relatively general. However, I can also restrict these to be Gaussians, right?
Yeah.
Then I'm staying within that. Then this would be a Gaussian manifold, but unnormalized Gaussian. I can further constrain them to be normalized Gaussian, but still their path might be outside the normalized Gaussian. I might decide first get out of the probability space and get back. Then I can further restrict this geodesic by adding a so-called partition function or something, just restrict myself to move within the probability Gaussian limits. So you can do, then eventually this becomes the canonical Fisher distance a lot of you work on. But it's also, you know, I personally have no, just a disclaimer, no strong opinion about which name to use. Just confusing to me, always different names, but my co-author has strong opinion about which name to use, especially if someone did their PhD in Germany, so they really prefer it. Okay. Yeah. Also want to talk about something that has been really popular in the machine learning literature, but I really wanted to talk about a bit about the mathematics of it. It's really what it really is, rather than just showing you, concentration results of such things. The idea is, I first use the usual integral operator. The idea is if I have a not very nice function, for example, this red sort of zigzagging line here, and I define an operator in here. For simplicity, I define the L2 to L2, and it would do is just to take a convolution with a smooth kernel, and this integral operator basically with respect to this measure rho will turn this not very nice function into a nicer function. Okay, you can also see the point of this is that every point here gets some information from the nearby points. And that's usually the idea for interacting particle systems, that where you are, you look at other particles, how they affect you. You look at one data sample, you also think about how the data samples nearby affect, like kernel density estimate. Okay, so this has been what's referred to as the maximum mean discrepancy. It's just a kernel discrepancy by measuring if you apply such an operation and compare the images of these two smooth image of these two densities or say measures, and then you take just the quadratic Hilbert norm, this weighted quadratic norm between mu0 and mu1, and with this interaction kernel or with this kernel. It can be, again, it's a L2 type of distance, so written down as a dual formulation. You can think about you have two bags of points. Now I'm not measuring the average Euclidean distance anymore. What I'm doing is try to find a smooth function, this kind of smooth function after the at the image of this integral operator that separate them. Okay, the amount of integrals this minus this, the best amount of separation is defined as maximum mean discrepancy. That's sort of what you can find in a lot of even nowadays textbooks, but I really wanted to cast this into a more mathematical understanding, is you can write it down just as a trivial distance because it's nothing but a weighted L2 distance. Then it can be written down in the same way, in a fashion that we have looked at before, just to write this down. You don't really need to write it down as a geodesic type of distance because the geodesics are simply straight lines, simply a flat space. Then you can really establish the connection.
So this guy is an integral operator, right?
Say it again. Which one? Right. So
it's not invertible, right? The inverse is
yes, that would be another question whether it's invertible or not.
Well, it's unbounded because it's compact, so it's unbounded.
If it's compact, if you actually have eigenvalue going to 0.
Yeah, it is but it's always compact, right?
Let's see.
It is always compact.
If it's positive, definitely it's always compact.
So can you go back to the previous slide? So you're
Sure.
assuming that it's in the this integral with the K, it's always compact.
Depends on the
At least
depends on the K.
Yeah, at least the things that we use in machine learning.
In machine learning, if you actually put into computational, well, it depends. The thing you actually use can be inverted.
Assumptions for this because it's actually if it is the
yeah, you could make the usual assumption. You can get compact. Usually for this purpose, you do think about a positive definite. You do think about positive definite kernel, which results in a compact operator. That's correct. The question is, I think
because if you want to have an RKHS, then you need to be positive definitely, and the operator is no longer compact. It's compact. Sorry.
It is compact. That's correct. Let me think.
Okay, we can talk.
No.
About
I have a.
This is actually
Yes.
that is a fundamental question.
This is a fundamental question. This is a formal. I do not mean this has a. I answered this question many times in my previous life, but now I couldn't remember what I usually say to people. I do not mean this. You can actually pop out a. How should I say it? Maybe I have to think about it later. You can think of this as a formal calculation. Okay, formal calculation means the epsilon delta has not been presented to you yet. You know what I mean? Epsilon delta language has not been presented to you yet. This is a formal calculation. Maybe you will encounter infinity. Does that make sense? Okay, so maybe.
No, we can talk about
15 minutes left, so
Oh, 15. Yeah, so I have to go. Yeah. Okay. The idea is not to study its inverse. The idea is to see the relation between the so-called maximum discrepancy and the Fisher-Rao, or say the Hellinger type of dynamics. Is to see that this, if you written down in this form, the so-called Riemannian tensor can be related in this sense that the MMD is recovered by the composition of the integral operator and the Riemannian tensor of the Fisher-Rao, or say the Hellinger, in the full measure space.
So GMD is also like what is GMD?
G is when you try to write the Riemannian formulation. This would be the Riemannian metric tensor.
So it's like a Riemannian metric.
You can think of it this way, but it's flat, so it doesn't make that much difference. It's independent of the state.
Okay.
The goal is to written down here. So this is why I write K inverse is to literally cancel this guy here. Yeah, so the goal is to see that it's a certain way of flattening the Riemannian tensor. And that's why it's also been very useful, is because about the calculation of this MMD. It's been very easy. So these two relations, you can compare them by relating by this, okay? So in a way, you can think about is if you kernelize the MMD, you get the Hellinger distance. The same actually happens if you try to kernelize the Wasserstein distance, you get the so-called Stein distance, which is also what people use in interacting particle systems for sampling. Okay, Thomas just said I'm running a little bit short on time, so I will from now on focus on the intuition. I'm very happy we can discuss, but I shouldn't go over time. Okay, so the thing I actually wanted to talk about, this is the first slide of it, is about generalizing the optimization algorithm to minimizing of a function, f of x. Think about generalizing gradient descent. And the implicit form of gradient descent is a proximal optimization algorithm. And as time goes to infinity, time goes to continuous time, discretization goes to zero, interval goes to zero, I recover the ordinary differential equation, right? So I'm going to skip off the jokes why the transpose need to be here, but if you know me, you have seen this before. The idea is that this is the gradient flow equation of the energy F in the space of RD, and with the geometry described by the probability space, okay? Now my goal is to generalize this to probability space, to have general purpose optimization algorithm over probability space, okay? So the rigorous attempt has been done in the literature in analysis of generalizing this to the Wasserstein space. For simplicity, think about replacing the Euclidean with the Wasserstein distance, replacing the F with a function of measures, and I minimize over probability measures. And this gives me the next time step. So my proposal is that you use this algorithm to replace the gradient descent to work in the probability space. As time goes to zero, I recover the so-called continuity equation. I call it the gradient flow equation of a system that's identified by the measures, by the measure space, by the energy functional that drives this system, by the dissipation geometry that tells you the mechanism of dissipation. These three things identify the gradient structure. And having a gradient structure is a way to identify the system that I don't necessarily need an equation or anything else. I just need these gradient ingredients to describe a dissipative system. Right? And this is the quote of Felix Auto, mostly going to skip in the interest of time, but these are the things I'm going to be looking for in using analysis tools to analyze optimization problem over probability distributions. Okay, how is this useful? Let's look at an example. We talked about generating samples of pi, right? Generate a model of sampling. The idea is that the goal is to generate a samples as if you're from pi, okay? You get new samples. The way to model is generate new samples. One way is to think about the stationary distribution of this Langevin stochastic differential equation. And at equilibrium, asymptotically, what I'm going to have is, I have an ODE that goes through this minus the gradient, right? The gradient descent scheme plus noise. At the end, I'm not going to collapse to a point. I'm going to hover around a distribution. And distribution is the equilibrium distribution of pi. Okay? So if pi is Gaussian, and every stage I'm still going to get Gaussian, right? So this becomes the typical dynamics of Gaussians. Now, if you look at, instead of the stochastic trajectory, because I'm adding noise, the density follows a deterministic evolution of the Fokker-Planck partial differential equation, okay? And as time goes to zero, we talked about or cover the continuous time dynamics. So this is the discrete time algorithm. And the goal of analysis, or say in the context for computation, is to think about, can I quantify the decay of the driving energy, for example, KL divergence. So in very good cases, just like linear convergence in optimization, you have global decay of KL. Depends on sometimes what geometry, what distance you put in here, what kind of properties pi has. Okay, maybe, yeah. Sure. Which part? This part, right? I will explain this in greater details in the future slides. But for this slide, this is just to say, if I run this optimization algorithm over probability distributions, over time, what I hope is this mu gets closer to pi. All right? So that's my goal, right? It's to model pi, okay? Now, this is an algorithm in the measure space in general. So every time I'm allowing you to move a little bit, this is like a gradient descent, okay? Now the goal is to think about this eventually. The best thing I can quantify, the best thing I can hope is this guy goes to zero. Of course, usually it doesn't happen in practice. The best thing I can hope for is the relative entropy will go to zero. In that case, I will be doing a good job. So here, what does it mean? This goes to zero. For example, you have evolving particles. Eventually, they form a distribution just like your target distribution. And I'm trying to quantify the decay of this objective function in optimization of the driving energy over a long time asymptotics, whether they decay exponentially or something. So this is the hope of to analyzing.
Why do you need exponential decay? Like, so
I don't need exponential decay.
Yeah, I was just trying to understand. So you want the final thing to go to zero?
Hopefully.
Maybe you want it to be bounded by some epsilon or something.
Yep.
But then the way you're writing this is not clear because you're saying in the beginning you're somewhere, and then at every time step you're exponentially below it. That's a very specific way to write it. Is there a reason for writing it in this way?
Is there a specific way reason to write it this way?
Okay.
Yeah. So basically, this would be the most. Let's just say this is you can go to a bit more to figure out other kinds of decay rate. Doesn't have to be exponential, but the exponential rate is the most. Let's just say. In a way, easy to characterize, or the thing people first realize the exponential decay is a consequence of, let's say, the pi having a special structure, so-called log concavity, or say you have a Gaussian distribution pi. This would be the most natural result for of this kind of structure. Is the exponential.
Scale and exponential, is it related somehow, or like do other distribution you choose something else there?
Like you mean pi. So it depends on what you choose at pi, as I will show. So it depends on the pi. You will have the property of pi gives you whether you can characterize this and what is this alpha. It's just like when you have a convex optimization problem, when you have a quadratic minimization problem. This precisely corresponds to the case when pi is a Gaussian distribution. That's kind of the results you get from quadratic convex optimization problem. Yeah. Okay, good. So we're running very short on time, so I could only talk about a few things, very high level, unfortunately. Sorry, should have hidden some slides earlier. The canonical idea of analyzing such exponential convergences through the so-called functional inequalities. So this is the typical case when you have pi e to the minus v. If you choose v as a quadratic function, of course, this will have a lower bound for the Hessian. Okay, so in this case, this lower bound for the Hessian lambda will determine a type of expression that's going to guarantee global convergence, global exponential convergence, as I have just shown. And this kind of inequality, in this case, particularly, it's written as the left-hand side is the Sobolev norm of the log score ratios, log grad Sobolev norm of the log density ratio, score difference. The right-hand side is a constant times the KL divergence. Okay, this is the most classical inequality, is so-called logarithmic Sobolev inequality. Now, this is guaranteed when your pi has this. When your pi is this property, basically this is the equivalence of a convex optimization here. This is an optimization problem of probability distribution. Okay, so essentially what it happens, think about it very abstractly. That's why I need to study these things in very abstract, because this is the fundamental thing. Just like you ask people, right? Initially, people ask, why is studying a function convex or not relevant? In the history of optimization, this wasn't always the thing people were interested in. It's when people really showed convexity has the natural result, then this generic topic of studying convexity has become popular. Here it's the same thing. This is basically a convex optimization problem in the Wasserstein space. It's going to give you this result. Manifest there is this inequality being true once you have this. But a lot of my work just goes to addressing what if I work on other spaces, like we talked about Hellinger space or put Wasserstein and Hellinger together. What if you have other divergences other than the KL divergences? How do we generalize these very intuitive optimization results to those spaces? Okay. For example, if you put KL, Hellinger, this is still not the Fisher natural gradient because I'm still working on general measures. We have complete characterizations of various kinds of decays. For example, for a Hellinger gradient flow, as time goes to 0, I'm gonna have this type of reaction dynamics. You move the measure, you destroy and create mass. An example is if you choose this driving energy to be the KL, okay? Then studying this is very easy because you just first write down the consequence of this functional inequality is this guy, you can immediately conclude there's no chance that you can get a positive number, that this L2 norm instead of the Sobolev norm can dominate the KL divergence times some multiple, right? So there is no the so-called gradient dominance. This what this inequality is called, because you can never grow mass where you don't really have mass. This is a simple consequence of the analysis. And in reality, what you can actually do when this is the KL is you can plug that in, take time to 0, and you can explicitly solve this ordinary differential equation. You write down the solution, then you realize that, okay, this measure eventually is going to become pi, unless this is stuck at 0. If it's stuck at 0, then the solution is 0. Okay, so you have many, many stationary solutions. So it also implies that the KL divergence is not convex in the Hellinger geometry. So I made a joke, but no time to tell. Okay, and it goes beyond to study the Wasserstein-Fischer-Rao distance. Basically, you try to combine the metric tensor of Wasserstein and Hellinger or Fischer-Rao. As you can see, some people call it Wasserstein-Fischer-Rao. Of course, there's a few variants. The idea is when you sample things, you can destroy mass and create new mass. Okay, you're allowed to efficiently transport. Of course, the most efficient transport is always to destroy the mass and transport whatever it's left, then create the mass later. And it will also result in different behavior if you do a further reduction to the parametric space, for example, a natural manifold. Okay, I'm not going to talk about all of them today, but just wanted to say we have a lot of tables and stuff in our papers about inequalities and so on, various nitty-gritties of constants and so on, worked out for different kinds of dissipations of different divergences in geometries. Okay, I just want to highlight one application. Sorry, going a little bit fast, but I just want to highlight one application is about minimizing the forward divergence, which I put mu on the second position. Sorry, I'm going a few minutes over time. I hope it's okay. Sorry, Thomas. I will skip some later topics. Just wanted to mention this. And I don't want to minimize this with the typical things I don't understand. Like there's a million things in base that people look at moment or propagation, whatever propagation it's called. I forgot. It doesn't matter. Yeah, it's what? It's not important. Well, maybe important historically, but I'm gonna just take a simple perspective of the Otto-Wasserstein gradient flow. Yeah, you realize that my co-author insisted there should be someone studied in Germany to name everything. So, okay, Otto gradient flow. So it's important to be in Germany once. Okay, yeah. Yeah, sorry, I had more jokes in my mind, but I'm not going to tell it. Okay, you write down the transport equation. This will be what's it look like, but this function here, instead of the score difference, you have the 1 minus the density ratio. And the typical idea is that if I cannot estimate this nicely, I would take some approximation approach, or say the smoothing approach. And this is the fundamental thing in non-parametric statistics. We try to limit it to some families. And what I will do here is just take the non-parametric approximation I talked about earlier, think about the integral operator, okay? And it's going to make this not very nice function inside nicer before I take the gradient. And after I take the integral operator, the gradient can be also taken to the smooth kernels. Now, the interesting thing for computation is this quantity can be actually estimated in practice, because in reality, this integral can be done in a Monte Carlo approximation by generating some samples from Z, or say you have some samples from your data. Then this quantity is estimated in reality as a functional approximation. But the important observation here is actually not about this approximation. It's about after you've done this approximation, this exactly becomes the Wasserstein flow of the maximum mean discrepancy. What does it mean? It means what I've been talked about earlier, this direct optimization problem over probability distributions. You can just apply this optimization problem with a different cost, which is the MMD, okay? If you do that, it directly gives this equivalence to approximation of the forward KL, okay? So I did not design a specific algorithmic framework to match the moments or try to do some important sampling, generate samples. What I actually do is directly cranking up this optimization problem in the Wasserstein space to minimize a different objective. And I theoretically showed this is approximating the earlier objective via this connection of the kernel methods or non-parametric methods with this minimization of the forward KL divergence, okay? So what you happen, you can just implement a type of sampling algorithm that works really by transporting all the points to fit a target distribution. And also wanted to mention a little bit, we talk about this relationship. Also, I want to think about the convergence. Easy way to build convergence, as we have done here previously, the algorithm you have seen actually has no convergence guarantees, is to establish similar functional inequalities to build the birth-death dynamics, birth-death mechanism into the transport mechanism, and then to perform the same smoothing property for the first part of the transport, but keep the birth-death there. And because of this guy has a nice structure, it's a simple ODE that converges exponentially, I can turn this kind of dynamics into the dynamics that I will destroy all the particles that can get stuck in non-convex or local minima and move everything towards the center. So that's the idea of doing an unbalanced transport. Is during the transport, I don't have to keep the mass there. I can kill some of the mass and turn some mass into the middle, right? Okay, so this is the resulting functional inequality. I'm just gonna skip. The idea is that you will have some exponential decay of the MMD, which can also be shown as a, actually, I don't have a slide. I didn't make a slide for it because MMD is actually also a Lyapunov function of a Fisher-Rao flow of the forward KL divergence. So if you track this quantity along the Fisher-Rao flow, the forward KL divergence in the whole measure space, sorry, it's very difficult to piece these things together. But the idea is that the MMD can serve as a Lyapunov function. This function decays over the gradient flow of the Fisher-Rao gradient flow of the forward KL. Yeah. Anyway, it's recorded. You can later transcribe it and figure out what I'm really talking about. You can put Fisher-Rao, Wasserstein Fisher-Rao into, just like you guys do, right? Fisher-Rao space and the Gaussian space can solve logistic regression problem. The idea here is I combine the dissipation of the transport and birth-death dynamics to get this kind of solution for the Bayesian inference problem. I don't really know what that word means, but as a Bayesian logistic regression solution, right? The goal is to see that not only you have the contribution of the Wasserstein part, if your target is Gaussian, the Wasserstein part contracts according to, the Wasserstein means alpha equals 1, beta equals 0, contracts according to the smallest eigenvalue of the target Hessian. Inverse, yeah. So that's how fast Wasserstein can be. But if you have the Fisher-Rao, this alpha equals 0. So the way we derive it, I'm sure it's not new, but it's just analyzing PDEs, ODEs. Just by looking at these, for the Fisher-Rao, this is irrelevant. You would have decay rate of just constant decay rate. But if you put Wasserstein and Fisher-Rao together, it helps you get through the places that one dynamics might have difficulty, right? So for non-Gaussian measure, unfortunately, current analysis, we still have to have a dependence on the log concavity constant, some future work to get rid of it, not too important in this slide. And also I wanted to say that despite the struggles of the regular KL divergence, if you flip them, things become much easier. The ODE can be shown just to be exponentially convergent, and this flipped KL is lambda convex, or say strongly convex in the Fisher-Rao space of Gaussian measures. So of course, how to implement it computationally is another question, which I don't deal with. All right, so that's the summary, right? So the goal of, I said in the beginning, the goal is to figure out a general purpose optimization problem, minimizing F. And sometimes I use this proximal formulation, find some suitable dissipation mechanism for this to happen, or for this distance of probability measure, or things like mirror descent, Wasserstein, and so on. And then in continuous time, I get the sort of a PDE, ODE in continuous time. Now the goal of to use these analysis point to take this abstract view is to eventually facilitate the analysis of the dynamics of optimization, sampling, and inference, okay? That's the goal, but I had to take a step back to figure out what people already know in mathematics, right? I'm not gonna in my lifetime invent all the nice mathematical advancements that happened over the past 20 years. What I'm gonna do is try to make relations to take what's useful for the dynamics of analyzing computational algorithms. And that's perhaps also as a belayed sort of comment to MT's questions, the first question earlier. And the simple results, we have analysis for the global exponential decay, or sometimes sub-level exponential decay, based on different geometries of Wasserstein or Fisher-Rao or Hellinger type, right? So if we choose different phi, the entropy generator function, my name for it, the convex function here, you can get different kinds of dissipation results, or sometimes not convergence results, right? So, and we also looked at an example forward reverse KL divergence for variational inference. Yep. Thank you very much for your attention. Also, I want to highlight that if there are some students, or some students in the audience looking for interested in such topics, I'm also looking for new group members in my new group in KTH in Stockholm. So, yeah.
Thank you very much for the talk. Are there any questions? Also, people on Zoom, feel free to ask questions in the chat.
Thank you for that talk. I want to know about the constant C in Knoxville context. So I think you mentioned that we can obtain the a type of loss-based equality in the case of Wasserstein and Fisher-Rao geometry. But I want to know about the difference between the constant Wasserstein and
Fisher-Rao. Great question. So I would first go back to maybe just the motivation. Everybody's on board about this is this in the standard case of the Wasserstein flow of the KL, which is the Langevin process or something. The C is basically the strong convexity constant you would have in convex optimization, right? It's bounding the smallest eigenvalue of the Hessian. So that determines the most difficult part of the dynamics, how it's going to converge, which is going to control the exponential rate. It would be just two times the smallest eigenvalue of the convex. So think about, you have just a quadratic function. The smallest diagonal, or even think easier, you have a diagonal quadratic function, okay? The smallest value on the diagonal would determine the convergence rate here. So this is the simplest case in the Wasserstein flow. Okay, so for the KL, things becomes difficult. Sorry, what am I talking about? For the Fisher-Rao flow, things becomes, or Hellinger flow, things become different. There's a lot of nitty-gritty, but I just want to give you some ideas to have a table somewhere. For the Fisher-Rao, basically, first I look at Hellinger flow on the positive measure space. And for this thing, it results in ordinary differential equation. And in fact, if you track, maybe let's say this is the ODE, right? Times some growth field. If every time you replace this mu by this replacement, let's just go here. If you just normalize this guy, this recovers the so-called probability flow in the Fisher-Rao full measure space. So for this guy, its convergence would not be determined by this diagonal matrix of that. So it's no longer in the same geometry. So the Wasserstein convexity has no implication in this case. In this case, what do we have? What we actually have is for the actual KL divergence, or say, if I choose this to be the KL divergence, actually I cannot have a decay exponentially throughout. I cannot have global decay. The reason is simple because you can look at it in different ways. It's just the typical way of establishing this inequality actually does not work anymore because the relationship between the derivative of phi prime and phi itself. But for a slightly different phi, for example, for the, let's call it forward KL, this generated function, which is the log divergence, what you would actually have global decay. So it depends on what kind of phi you can choose here. Remember, I have a picture in the beginning. You have different kinds of slopes in this entropy generator. The slope actually translate into also related to MT's question, right? You can actually define the quantity equivalent to a slope in the metric space, and you can explicitly calculate the slope in the probability space. And that slope is actually going to be 0 for the KL divergence. That's why it can get stuck in a non-convex optimization in the sense of the convexity in the Fisher-Rao space, not in the Wasserstein space. So that would be a different kinds of results of convergence there. So, and let me just show. And for the, these were the constants we can characterize here. This P basically depends on if you use this, usually people call it P relative entropy, this 0 divergence, 1 divergence. Different phi will have different slopes will determine the convergence in the Hellinger space or the Fisher-Rao space. Now that's just that. There are also other more nuanced analysis. For example, the results I'm characterizing here are the global convergence result. For example, if you think about an optimization problem, you have a convex optimization problem, or say quadratic problem. Its convergence rate can be characterized globally because the Hessian is constant. But there are cases if you have non-quadratic functions, somewhere convergence faster, somewhere convergence not so fast, but as long as it behaves well at where you're interested in, you can still make the analysis of within the sub-level sets, right? So if you think about this thing, maybe you're only interested in the sub-level here. You're not interested in things outside, or you can assume some growth outside. So there, we also characterize this sort of sub-level results somewhere, but it's a little bit more nuanced, but you usually get better results if you consider a sub-level kind of convergence. The things we characterize in this paper are global convergence. For example, the Barclay-Emery theorem, the classical results of Barclay-Emery is about a global convergence, spectral gap. Yep.
Are there any other questions? Okay, there's no more questions. Let's thank Jia-Jie again.